We need Maxwell to help out with this many body problem here. Good afternoon. Welcome to Inspiring Brilliance, celebrating the legacy and genius of James Clerk Maxwell, being broadcast to you live, direct from the Royal Society of Edinburgh. I'm Jim Raudio, the chair of the afternoon session, and I will be introducing our first speaker. We'll be providing a demonstration of Maxwell, color vision, and the future of digital communications. This first speaker will be Peter Reid, from Planning and Communications Project Manager, University of Edinburgh, and the second speaker will be Professor Harald Haas, Chair of the Mobile Communications School of Engineering, University of Edinburgh. Peter?
Thank you. This is by way of being, excuse me while I do this. There we go. This is by way of being a tale of scientific serendipity. It's how you can get the right results by doing the wrong things. It's also a tale of scientific detective work, how in the 20th century we were able to work out just how Maxwell, and by the way I should apologize, Clerk Maxwell, managed to achieve in the 19th the seemingly impossible. The whole of the three-color model that Maxwell was working on is based on, or predicated upon, the evolutionary structure of the human eye. There are, to simplify, three basic color receptors in the eye: red, green, and blue. And if you fire a red photon into the eye, then you activate the red receptor. Of course, you can see from these curves, which show the sensitivities of these receptors, that they overlap quite a bit. They're quite wide. So if you fire a yellow photon into the eye, the red and the green receptors react. And the brain interprets this as a yellow light. And we can use that evolutionary quirk of the human eye to fool it by, for example, firing a red and a green photon into the eye, which then has to see it as yellow. Now, I can illustrate that with an example of what Malcolm Longear in his wonderful talk showed as well with his little box. Three circles, which are red, green, and blue, and they are only red, green, and blue. There are no other colors on the screen. And the experiment for you to do now is to see if you can not see the other colors, because there are only red, green, and blue photons coming out of that screen at your eyes. But it's impossible for you to not see, I hope, that this is, color blindness notwithstanding, that this is a white disk. And it was this that Maxwell was wanting to demonstrate when he had been doing his qualitative work and his quantitative work on color vision at the Royal Institution in 1861. Now, the little color disk that Malcolm Longear had, it's wonderful to see, but it's too small for a big demonstration. The light box which Maxwell developed to do his very, very sophisticated numerical work wasn't bright enough for this kind of venue. So Maxwell thought what he could do was take a color image of a color object, and I've got here a modern ribbon, and he could take three photographs of this, one using a red filter, one using a green, and one using a blue, to produce three black and white images, and then recombine those black and white images using the same filters. The idea being that he would replicate the red, green, and blue colors that were used in this original object. Now, this is obviously a modern version, but these are the original plates, or copies of them anyway, held by the Maxwell Foundation, taken by Thomas Sutton, a well-known photographer in the mid-19th century. And I was lucky enough to be able to get copies of these to make very high resolution and high contrast scans of these ribbon images, which I was then able to use for my demonstrations. Now, one of the things that Maxwell did was he projected his images using magic lanterns, and unfortunately I wanted to do the original demonstration, but I couldn't find three magic lanterns. And at the back of the theatre, unfortunately we can't have it at the front, are three old-fashioned slide projectors in which we've mounted the three monochrome slides produced by Thomas Sutton for Maxwell. Now, I mentioned color filters. Of course, there were no such things at that time. There was no color photography. And what Sutton had to do was he had to work out how to make filters that he could use for his, both for recording and projecting the images. And we have notes of what chemicals he used. And so I wanted to make replicas of these. And what we have here are glass plates, pairs of glass plates with a very thin layer in between, into which I was able to inject chemicals which would then act as filters in order to either record or project an image. And so it was with these filters and the 3 monochrome slides and the 3 magic lanterns that James Clerk Maxwell went in May of 1861 to the Royal Institution in London and carried out this demonstration, which we're now going to repeat for you now. So I'll just turn the lights off. Oops. The first slide which we'll see is the original, monochrome slide produced by Thomas Sutton when he used the ferric thiocyanate, or red filter. So this is the red component, which we can now see by placing the red filter in front of it. This is the red component of that ribbon's image. Similarly, if we now look at the next slide, is that the green one? Yes. This is the slide that was produced by Sutton using the copper chloride solution, which is a green compound, and if we now place our filter in front of it, we can see the green image. And finally, we also have the blue version, which is copper sulfate, and if we place the filter over that, we can see the blue component. Now, these are 3 fairly dark images. One of the things that we have here is that the projector is quite far back, so it's a little dim. And so what Maxwell did then was to reverse that process. He showed the blue image, and then he slowly took away the green filter cover to superimpose the green and the blue images together. Now, this was the first time that this had been done, and so on the 17th of May of 1861, the people in the Royal Institution were the very first people in the world to see the combination of the 3 colors of the original ribbon as the human visual system perceives it. And this was what Maxwell displayed to that audience then. Or so you would think, because it wasn't like that. It was impossible for this image to be produced. It could not be done. People tried to replicate it, and they failed. This was absolutely impossible with the materials of the mid-19th century. Now, to look into that in any more detail, thank you, Sabine. We need to do some detective work, as I said. In the early 1960s, for the 100th anniversary, I think, of the Maxwell ribbon, some work was done in the US to actually try and discover why this had worked when there was no way it should have done. And we know there's no way it should have done because we know what materials were used at the time. This is a spectrum, as you can see at the bottom, and the curve you can see here is the transmission curve for ferric thiocyanate. It's the red transmission curve. It tells you that it's passing through mostly red light. This is the one for copper chloride, and this is the one for copper sulfate, which is absolutely fine. This is what we'd expect. The trouble comes when we superimpose this curve. This represents the sensitivity of the photographic emulsions that were available to Maxwell and Sutton in the mid-1850s. To ram the point home, that's the only colors that could possibly be recorded by the emulsions of that time. A bit of blue, a teeny wee bit of green, and conspicuously no red whatsoever. And yet, we have this image, which shouldn't be like this. What Sutton should have got was that. And yet he got a red image. Now, very quickly to go back here, we do have notes from Sutton's experiments, and he does say, he does back this up in some extent. He says his exposure time for the blue image was 6 seconds. His exposure time for the green image was 12 minutes, which gives you an idea that the energy levels were much, much lower in terms of activating the emulsion. But he still got a red image. He still got this image, which was about 8 minutes, when he shouldn't have done. So the problem is, of course, it looked like it wasn't possible. Now, in our modern, conspiracy-driven, internet-mediated, set blatter, fake the moon landings world that we inhabit, it's quite obvious what would happen immediately after that. We'd have something like this, which would immediately come out, and people would say, it's insane. Somebody asked me to tell, somebody said, I'm old. He said, tell the grandparents in the audience, this is something on the internet. So there you go. But this is the kind of thing that we would do now. Immediately people would say it was nonsense. They would come up with all sorts of theories, it was aliens and everything else. But the problem remains, it was not possible for them to have produced that image. And this is where the detective work comes in, because this is where the American researchers looked into the materials that were actually available at the time and made one of the most wonderful discoveries. I said before that you now can't see it very well because of the light, but the ferric thiocyanate curve is completely blocked out. It's not available. The photons aren't energetic enough to activate the emulsion. But with modern analytical techniques, we can look at these chemicals and we can establish the bandwidth of their transmission properties much more widely. And it turns out that ferric thiocyanate has a tiny little window up in the ultraviolet, beyond visible light. We also know what red chemicals, red dye stocks were available in the 19th century. We can either obtain those or we can recreate them. And again, we can apply techniques to the transmission, to the reflection properties of these dyes. So we can actually see what light is reflected from the red dyes of that time. And hey presto, if we look at that, the red dyes that were used in cloth making at that point, and which were probably in that ribbon, also had a little window in the ultraviolet. Now, I was going to say that ultraviolet colours are not new. We all look at flowers and think they're lovely, but of course flowers have been co-evolving with pollinating insects for tens of millions of years. And to a bee, a flower has target indicators in there saying this is where the nectar is, and these are visible only in ultraviolet light. So UV colours are not anything new. But this then is not an image of the red ribbon. This is an image of the ultraviolet ribbon, but it happens to be the same one as on the red ribbon. And with one bound, they were free. Now, that's convincing, but not necessarily conclusive. There's one last thing we can do, is to really be sure that that's what happened, is we can look at the images in close-up. And we can see, if you look at the red image, you'll see that the red image is considerably more blurred than the other two. Now, Sutton was a very, very experienced photographer. And this wasn't exactly the hardest thing in the world to photograph, a still image. And yet, he seemed to get this wrong. And of course, the problem is, what was he photographing? Now, these are the original plates, which are actually rectangular. But what you see here are the circles, which actually demarcate the lens that was used to make the images. So this is actually the edge of the recorded image. What I did was measure these, the red, green, and the blue ones. And we know from the type of camera that Sutton used that he moved the lens back and forwards. And we can actually see, if we superimpose those, I hope you can see that as red on the outside, green, and then blue, which is what we would expect from focusing the image slowly to focus on each of the colors. But we know that he wasn't photographing the red, he was photographing the ultraviolet. And that's what the focus ring would be for the ultraviolet image. So Sutton was accurately and probably frustratingly focusing a sharp red image, and then in the darkroom was producing this blurred photograph, which he must have scratched his head. I just imagine Maxwell, you call yourself a photographer. It's rubbish. He's going, look, he says, I honestly, they were all sharp when I took them. If he had been a bee, if we had evolved from bees, then of course we'd be saying it was a tremendous image. We wouldn't have any problems. So it's a wonderful example, and this is just a static representation of the original image, but for me this is just the most wonderful example of how science can really work. They used the wrong plate that didn't do any, that couldn't possibly have worked. But then they used a ribbon that happened to make use of one dye that had one little window where it reflected UV. I should have said that they used sunlight to illuminate the ribbon full of UV. And then they used a chemical that, completely unbeknownst to them, happened to have a little transmission window in exactly the same part of the ultraviolet spectrum, so that it recorded the UV light helpfully given off by the red dye. And they produced the image. Sometimes in science, you get all the breaks. And I just think it's nice to see that occasionally. Now, this, just really to conclude, this is often slightly misrepresented as being the world's first colour photograph. It isn't. It is in as much as that it reflects a permanent reproduction of a three-colour process used to make a colour image. But it's not really the way we do photographs now. And I think calling it that actually misses the true legacy of the work that Maxwell did on the three-colour theory. I come back actually to this, because this is, as I said, red, green, and blue photons. There are no other colours on that screen. We are making the other colours because we are integrating these within our visual system to see those spectral colours. And to illustrate that and why that is the case, this is a photograph of my monitor in my office with the Trinity College portrait of Maxwell. I chose that because, not just because it's Maxwell, but because it's all creams and browns and whites and blacks. No red, greens, or blues in there. Now, I photographed this, and then, because of the camera at a reasonable resolution, we can zoom in. and some of you may see the structure there, but you certainly should see it when we do this. You begin to see the integral structure of the picture elements, the pixels that make up the image. Now, these are still all creams and browns and blacks, and that's the limit of my camera's resolution, but I had a USB, not very good USB microscope, which I placed onto the monitor, and we could then use the zoom, the magnification of that, to begin to see the actual structure of the pixels that make up that image. And this is the white part of his eye, under his eye. And if we really go to full detail, what we see at the basic atomic level, if you like, of any display are the little Maxwell triples, the red, the green, and the blue, sitting there, just making up our images. And these can be varied in intensity, just like Maxwell did with his color disc, just like he did with his light box, to make a whole gamut of different colors. And so every single person in this room probably has a display in their pocket which makes use of this property. Every smartphone, every laptop, every tablet, every television, every display device, projective device, owes its operation to that work and the legacy of James Clerk Maxwell. And I think that's a fitting way to think of his work rather than it being the first color photograph. Well, that's the past, and which is his original work, and the present, which is the ubiquity of the devices that actually make use of it. What I'd like to do now for the next 15 minutes is hand over to my colleague, Professor Harald Haas from the School of Engineering, who's going to talk about how that three-color theory and others have a legacy in the future of digital communications. Thank you.
Yeah, good afternoon, ladies and gentlemen. It's my pleasure to explain today how Maxwell's or Clerk Maxwell's theory on colors combined with its theory on electromagnetism and wave and fields combined could transform the 21st century of mobile communications. So it is clear that it would have not been possible without Maxwell's work to have this revolution of smartphones. So smartphones are now everywhere. It's a utility like electricity and water, which we need in the same and use in the same way. And in fact, there are more smartphones on this planet than human beings. And this trend is set to increase. It's not only that we have so many smartphones, the amount of data that we transmit through mobile networks is staggering. So by 2018, people forecast that we send the equivalent amount of data through our mobile networks, which equals 1.8 million years of high-definition video through mobile networks every month. That's by 2018. This is with all your YouTubes, with all the video streaming we're having now, and so on. By 2020, what we will have is a slight shift in gears. At the moment, we have mobiles and humans that communicate wirelessly, but we have the driverless car on the horizon. We have the things and the objects that will be connected to the Internet of Things. And now what we see by 2020, so 5 years from now, 26 billion wirelessly connected devices on the planet, out of which are 9 billion mobile phones, so you see a moderate increase. We have, however, 10 billion of consumer electronics that are connected wirelessly. And obviously 7 billion machine-to-machine communication devices that we have out there. And so far, all these wirelessly connected devices use a part of the electromagnetic spectrum, in particular, the radio waves and the microwaves. This is what's used in all these systems. So the question is now, do we have enough resources to cope with this exponential increase of data traffic? Now have a closer look at the spectrum. And the radio spectrum, we see, ranges from 3 kilohertz to 300 gigahertz. Obviously, we have various wireless services like radio. We have terrestrial communications, TV, 3G, satellite communications, and every service uses a very small part of that spectrum, and it's very rigidly divided. So if we looked at this image here, it would say, okay, there's not a problem. There's enough white space or red space that we can use. But the reality looks like this. This is the frequency map of the United States of that spectrum. And this patchwork is that somebody has its finger on some part of the spectrum. And it's not only that it's completely divided up, there's also something like hot seating going on. Some of the spectrum, here you see multiple squares, is reused. So some people use it at daytime, others use it at nighttime. So we have this hot seating going on. And now, as an engineer, you get worried. We want to serve the world with more wireless connectivity in order to save the planet, to make our environment smarter, so reduce CO2 emissions and so on, but we don't have the means of doing that. And this is the point where Maxwell's pioneering work on color theory comes in, because if we step back and look out of the box and say the radio spectrum is only one part of the electromagnetic spectrum, obviously we have much more available. And there's a little stripe, a little part here, which is the rainbow colors, the visible light spectrum. It appears to be tiny compared to the radio spectrum, but all of you know this is because we plotted in log scale. If we plotted the spectrum in its real, then first of all, let's see how we occupy the current radio spectrum. This is it, how it's occupied. And now if you plot in the real term, in fact, there's 300 terahertz of visible light spectrum, and it is a factor 1,000 times bigger than the entire radio spectrum. And now the question is, there's a big pool. Basically, we have found a new oil well for data communication. Can we make use of it? Can we utilize it? Yes, we can, but if we go back to affiliated gentleman and inventor Edison here with a light bulb, the incandescent light bulb would not be possible to use because the fact we cannot really modulate the light bulb. But we have the LED, the light emitting diode. It's an electronic device that produces photons via a physical process, and which I briefly described. So the LED is a glass bulb. Inside there's a little metal cup. Inside that metal cup is a semiconductor, a P and N doped semiconductor. And if we apply a voltage across the terminals, what will happen, so these are the terminals, what will happen that we have a recombination process, and energy is released in the form of photons if it's the right energy level, the right materials. And that process of recombination and release of photons emits light. So the question now is, okay, we have LEDs in various colors, but for a long time we only had red and green LEDs, and as we know from previous work with red and green, we can't create white light that we have in our rooms here. And it took quite some time to develop the blue LED, and these gentlemen is Nakamura, Akasaki, and Amano, who got the Nobel Prize in Physics, as we know, in 2014 for the invention of the blue LED. And that really triggered the revolution of LED lights that are much more energy safe than, require much less energy than the incandescent light. So this is the white LED light that we have. Now, the real question is, with that light, can we transmit data with that LED light? And yes, we can, because it's an electronic device. We can therefore change the intensity in a very fast manner, up to hundreds of megahertz in terms of frequency. We can modulate that LED. And that's something that I coined in a talk, a TED talk in 2011, as Li-Fi, in analogy to Wi-Fi. The principle is this: we have a video content, any video content, we have digital content, any digital content. It flows to the LED. The brightness of the LED is changed in accord with the binary ones and zeros. So if you want to transmit a 1, we turn it on, a 0, turn it off. And we have a receiver which will receive that signal, and then we decode that content. Obviously, we have developed techniques that are much more advanced as compared to this on-off keying in order to really get high speed, and we have shown that we can get speeds up to 100 gigabit per second. Now, let me combine that with the color theory, and what Peter has just shown is we have the three colors. Now, would it be possible with white light that we encode independent data streams on each color? We call this wavelength division multiplexing. It's used in fiber optics, but fiber optics is a very a nice medium, it's glass, and there's the propagation is clear. In the ether, the conditions are not as good as in glass or in fiber. We have reflections, absorption, and so on. But the question is, can we do that? Have independent data streams, combine them into white light as an RGB LED, and then have that light source sorry, I better do this again. So we have the 3 data streams, combine them into white light in the middle, and have white light transmitting 3 independent video streams, as we show here. So we have 3 data streams represented by the 3 colors. And what I'm going to do now is I'm going to demonstrate that. So we have the modern version of Clerk Maxwell's light box here. There are 3, what we have here is 3 laser sources with a mirror system, and we have a combiner, and then have a diffuser in order to create a white light beam. And what you see there is 3 boxes, and each box has a color filter, as Peter shown, and selecting out the respective channel, the respective color channel, which carries a video each. So now what you see is RGB sending 3 different videos from a white light beam. So let me now turn off the red, and then what you will see is that the first laptop will stop if I turn on the red channel. Turn off the red channel. On this, you see that stopping. I turn it on again, and the red channel will resume. Now I can turn off the green channel, which is that laptop there at the corner. I turn the green channel off, and what you will notice is that the green video will stop. And I can turn it on again, and after some time, that video will resume again. And then we have the blue. This is the middle laptop. You see that lecture going on. I can turn off the blue channel, and the video will stop. And if I turn it on again, the blue video will resume, as we see now. And these 3 independent data streams are really transmitted by a single white light beam that you see here, showing out of cardboard. And you see at the edges a bit of the green and blue and the red. So this is how and I think this is the first time we've shown that in public, a real wavelength division multiplexing system using the ether, using the air to transmit the data content. If you want, have a close look into the modern light box we have here. So what is this is fairly complex, but in a few years from now, you will have this hopefully in your smartphone. You can get your imagination. So what we have is 3 boxes here. These are 3 modems. You see them here blinking. You have the Ethernet cables going into these boxes. And these are not Wi-Fi routers. These are Li-Fi routers. Obviously, there's no antenna involved. And then we have a red laser, a blue laser, and a green laser. We have collimation lenses here. In the middle, you see the lenses. And we have mirrors. And we combine the light beam into a white light beam, very narrow needle beam. And I have a diffuser in order to create this white cone. And then this is transmitting the 3 videos, that system. And a similar system you have in BMW car headlights. And this will be the future of future illumination. So the question really is, in the future, can your lights give you all the high-speed internet you need in the future to do all the fancy and nice things that will change the world? Thank you.
Thank you, Harold, Peter. So that we had the full 30 minutes for this presentation, there won't be any questions. But Peter and Harold will both be around during breaks and such. And also the demonstration will be going on all afternoon. You're welcome to come up when other speakers aren't presenting and check it out. Our next speaker today will be speaking on the impact on engineering of Maxwell's articles on structural mechanics.